Consider a particle moving along the spiral helix r of t equals 4t, 5 sine 2t, 5 cosine 2t, and find the velocity and acceleration vectors and decompose the acceleration into its tangential and normal components. So we've previously studied this spiral helix and we found that the curvature is constant. It is 5/29. The formula for the unit tangent vector at any point is given here, 1 over root 29 times the vector 2, 5 cosine 2t, negative 5 sine 2t. And the normal vector at any point is, the unit normal vector is given by 0, negative sine 2t, negative cosine 2t. And this formula is the formula for the breakdown of the acceleration into its tangential and normal components. So first we'll calculate the velocity vector. The velocity vector is simply r prime of t, and that would be 4 10 cosine 2t, negative 10 sine 2t, and the acceleration vector is the derivative of the velocity vector, or the second derivative of the position vector for the curve, and that would be 0, negative 20 sine 2t, and negative 20 cosine 2t. Okay, so we have a velocity vector and we have an acceleration vector. Notice that the acceleration vector at any point is pointed towards it looks like the x-axis. And now we can decompose. So in order to decompose, we need the curvature here, which is 5/29. We need the derivative of the magnitude of the velocity vector. So the magnitude of the velocity vector is the speed of the curve, and that would be, and we need the derivative of that. So the magnitude here is the square root of, it looks like it's going to be a constant, and so v prime is going to be 0. Let's see, the magnitude of v of t is going to be the square root of 4 squared, which of course is 16, and then this one squared plus this one squared is just 100. So this is the square root of 116, also known as 2 times the square root of 29. So that's the speed of the curve. It has constant speed, and so the derivative of the speed here is 0. Okay, so there is no tangential component of the acceleration because it's got constant speed, so the curve is not accelerating in the direction in which it is moving. The only acceleration that is happening is because the curve is bending, and so you're getting a radial acceleration, and that is given by the curvature times the square of the magnitude of the speed, which we also know now. The magnitude of the speed being 2 root 29 or root 116, its square is 116. So the acceleration vector breaks down into, we have 5/29 for the curvature times the square of the speed, which is 116, and then times this normal vector, 0, negative 20 sine 2t, negative 20 cosine 2t. And of course the 29 here cancels, making a 4, and we have 20, so we can factor out a 20 and make it 400, or negative 400 times 0 sine 2t cosine 2t. So we have decomposed the acceleration. It's just a multiple of the normal vector in this case because the tangential component was 0.